Okay, in my video, I'm going to give you a general overview of what polysaccharides are, what are their functions, um, its solubility, what it looks like, which is also in reference to what it is, and some foods that are commonly used in the food industry to create specific products that might use polysaccharides. So to begin, polysaccharides, I'm going to draw this out for you, are large, simple sugars, well, complex carbohydrates, technically, and they're made up of glucose units. I'll show you. Just for ease and simplicity, I'll just draw simple structures, just a chain here. Okay, so for example, this whole structure would be a polysaccharide, but each structure within the polysaccharide is a monomer, a glucose monomer, and each small glucose monomer makes up a polysaccharide, which makes it a complex carbohydrate. So we have these ring structures. A polysaccharide is broken down into, I'm going to go into starches, which is the plant form of a polysaccharide, and they're broken down into two subunits, amylose and amylopectin. Both starches, well, I should say both carbohydrates, are very well known and used in the food industry. Can you see that? Yeah. So I'm going to erase this and go into amylose and amylopectin. So amylose, which is probably 20 to 30% of all starch products, that this molecule here is what makes up about 20 to 30%, and amylopectin, which I'll go into further in this discussion, is about 70 to 80% of most food products, and that one makes up most of our caloric intake in our diet as humans. So amylose is a linear structure. Sometimes it can be helical, such as this right here. Is that seen? Sorry for the report. And these are made up of glucose units as well. I'm just going to draw something in there for simple illustrations. And these usually have one reducing end and no non-reducing ends, and the viscosity of this structure is not that not likely, as opposed to amylopectin, which are branched structures. Can this be seen? Amylopectin. Try to draw it bigger. Which has one non-reducing one reducing and many non-reducing ends, and this is amylopectin. And with this structure, it's very viscous upon heating, and like I said, it makes up about 70 to 80% of most foods that undergo gelatinization, that may be used for emulsifiers, thickeners, you name it, when it comes to processing. This is the more common structure that will be used. One's a little messy. And waxy cornstarch is one of the main forms of amylopectin that would be used and heated during gelatinization for that. For these polymers, if you can remember what I drew originally, they're made up of glycan, those small hexagonal shapes that made up the entire polysaccharide. I can draw it again for you. They are these ring structures here. This polysaccharide is typically made up of more than 10 of these hexagonal shapes. A monosaccharide and a disaccharide and an oligosaccharide will either have 10 or less than that, and the polysaccharides exceed those, and those are pretty much the complex carbohydrates, which are some of di and oligosaccharides combined. If you think of the name poly meaning many, that prefix, and saccharides kind of explains what a polysaccharide is. Some of the functional properties, like I said, are that they are very good gelling agents if heated correctly and adjusted with the right pHs, for example, and say like a pectin formulation or confectionery products. Well, not with pH with that, but those would be really good for gelling. It's a good thickener, emulsifier, and it also holds water well, even though it is technically water insoluble unless it's been placed in cold water. There are also gelling functionalities, well, not gelling functionalities, functions that exhibit different types of gel formations within polysaccharides. For example, you have 3 of them total. You have your hydrogen bonding, your ionic bonding, and what's the other one? Ionic bonding, hydrogen, ionic, and hydrophobic bonding. And with each of these 3 types of bonding of gel formations, there are specific characteristics that are illustrated within. For example, with hydrogen bonding, they create junction zones through hydrogen bonding. Ionic bonding forms egg structures. There's usually calcium within the between both of the parallel structures, and this forms egg crate structures. So essentially, that's your calcium. Essentially, those 2 molecules are compacted together through ionic bonding. Ion thinking the calcium and these hydrogen bonds, so they kind of come together through that mechanism. And you also have hydrophilic, and as the name explains, hydrophobic bonds, which are water hating or what have you, kind of come closer together. So you may have, I'm just gonna make up something here. You may have like a you may have hydrophobic. You may have a hydrophobic interior and a hydrophilic exterior, and but you know, let's make that the other way around so you can actually see it. So let's just say you have a hydrophilic interior and a hydrophobic exterior. So the insides of this structure will, like the ionic structure, come back together because they're trying to keep out water, H2O, and by doing that they form structures as well within the inside of their structure, and the outside, because they're hydrophobic, they kind of contract from one another and find safety from water itself. That was a brief overview of what polysaccharides look like, how they may be used, where you might find them used in the food industry, and gel formations of polysaccharides in the industry. Thank you for watching.